Okay. Thank you, everyone, for joining us today for the University of Texas at Austin Energy Symposium, sponsored by the Energy Institute. I'm Carrie King, research scientist and assistant director at the Energy Institute. And before I introduce today's speaker, I will point out the next two upcoming talks, which I suppose are getting fairly related. The next one is on carbon capture and storage, so CCS, the Swiss Army knife of climate change. This will be discussed by our own Alex Bump, who is a research geologist at the Bureau of Economic Geology here at the University of Texas. And then the following week will be another research scientist at the BEG here at UT Austin, Peter Eichabel, and that will be on storing hydrogen. So after today, we're going to learn about storing molecules underground even more. So with that introduction, I will now is pleased to introduce Roger Aines. He's chief scientist of the Energy and Homeland Security Program at Lawrence Livermore National Laboratory. His talk title is Science and Engineering of Negative Emissions Technologies. So we're going to capture these things, and then our next 2 weeks are going to discuss perhaps sticking carbon and other molecules underground. So a little bit more background on Roger. He leads the Carbon Initiative at Lawrence Livermore National Labs, which aims to understand, develop, and implement technologies for the removal of carbon dioxide from the atmosphere, or so-called negative emissions technologies. He's been at the lab since 1984, worked on nuclear waste disposal, environmental remediation, stochastic methods to inversion and data fusion, management of carbon emissions, and other things. He has authored the recently released book, Championing Science, a book that helps scientists communicate more effectively with decision makers. So he's going to communicate with us today. Hopefully we are all making important decisions based upon what he tells us going forward. The abstract of his talk, we will need to remove enormous amounts of carbon dioxide from the air if we are to come close to our desired temperature targets. Science and engineering behind these removal methods is incredibly varied, and this is an opportunity for advances and a responsibility for technologists to consider not just energy efficiency, cost, and other technical parameters, but also how cleaning up the atmosphere will affect people's lives. So he will discuss with these different technologies and opportunities for negative emissions technologies. So with that being said, I'll stop sharing my screen and hand it over to Roger. For those of you viewing, as always, please enter your questions into the question and answer section of Zoom chat or on YouTube, and I will look to ask these questions to Roger at the end of his talk. And if you have a clarifying question, try to submit that when you can, and I will try to interject as possible. All right, thank you.
Thank you, Carrie. Thank you for the introduction. Welcome to all of you. It's a great pleasure. I'm sorry I couldn't join you in person, but look at how many more interactions we get to have by doing it this way. So I'm going to share my screen now, which always the challenging part. Okay, so let's jump right in to what's happening in our climate and why we have to worry about something called negative emissions. This is the arc of greenhouse gas emissions that'll happen if we basically keep doing what we're already doing. And we all know what kind of negative outcomes that's going to result in. Well, done some pretty good modeling that says if we want to get below 2 degrees C, or even if we want to get to 1.5 degrees C, which is an ambitious target, we're going to have to get to zero. We're going to have to get to the point where we're not emitting greenhouse gases anymore, or more importantly, where we're at net zero greenhouse gases. What do we mean by that? It's a pretty simple mathematical concept. There's everything we can do to mitigate the greenhouse gas emissions is in the technologies that you're already talking about, technologies that you're going to hear about in the next 2 talks in this series. And those are not going to be enough. That's the conventional role of CCS that we've all seen and heard about. And certainly BEG is a really important contributor to that science and technology. But the reason that doesn't go down to zero is that there are some other things that we're going to have to consider besides electrification, besides carbon capture, besides efficiency. And basically, there are other greenhouse gases that we're not going to be able to eliminate by those approaches. And there is going to be some CO2 that we simply, it just takes too long. It's too hard to squeeze out of the economy no matter what. One of those, airplanes, going to be very difficult to fly large aircraft, long distances without liquid fuels. But perhaps a more insidious one is agriculture, not the fuel to drive the tractor, but the fertilizer coming off the back of that spreader. The nitrous oxides that are a natural result of spreading fertilizer on agricultural land account for about 1% of our worldwide greenhouse gas heating effect today. And we're not going to be able to live without that. We could only feed about half the world's population if we didn't have fertilizers to increase our agricultural production. So that's one of the things that we're not going to be able to get rid of. It's going to be part of those, what we call residual emissions. And of course, there's the emissions, the methane that come from other aspects of agriculture, in particular from cattle. Are we going to live without meat? Are we going to live without fertilizer? Those are decisions that we could make, but I don't think we're going to. I think those are going to be part of the residual emissions, both the other greenhouse gases and the CO2 that you see on this graph. So the technologies that I'm going to talk about today are going to address two kinds of problems. These reductions in residual emissions. If we have to get to zero, if the models tell us we have to get to zero to hit the temperature targets, how are we going to subtract something from the atmosphere when we haven't been able to stop emitting? And those reductions are going to be almost certainly all carbon dioxide. So we're going to have to remove carbon dioxide in order to balance the emissions that we still have. And of course, there's the net effect that we've already too late. We've already put too much CO2 in the atmosphere, and we're going to have to remove some of that. And this green area on the chart is an estimate of what we're going to have to do for gross negative CO2 emissions. And of course, we can't just start in the end of the century. We're going to have to start now building up, because these things are going to take a long time to build up. It's important to recognize that the number for 2050 there, on the order of 10 billion tons of removals per year, is twice the size of the global oil industry today. The global oil industry moves about 5 billion tons of oil. And so between now and 2050, we have to create global industry that's twice the size of today's oil industry. It's a huge lift. It's going to be something that all of you are going to participate in. It's going to be part of your lives, and hopefully you're going to solve that problem. So I'm here to try and motivate that. I do want to point out, though, that the range of options is very large. The models tell us that there's a lot of different things that we could do, including some models that tell us we wouldn't need to remove carbon dioxide from the atmosphere. And all of those models involve precipitous changes in our economy today, almost instantaneous stopping of using of fossil fuels. And so I don't think those are likely to happen. These middle changes, the middle number of models that you see here that lead up to removals on the order of 10 to 15 billion tons by the end of the century are, I think, much more likely. And in fact, probably the higher level ones are even more likely that we're not reducing our emissions as fast as these models tell us we should. And we may have to remove more than 10 billion tons, maybe 20, 25 billion tons of unimaginable amounts of CO2 that we have to remove in order to hit the temperature targets and avoid the largest impacts of global warming. Well, how can we do it? I'm going to walk you through three methods for removing carbon dioxide from the air, all of which have engineering applications, but all of which need to be considered jointly. You can't look at any one of these and say it operates independently of the others. That's not how people think about problems like this. If you talk about any one of these, there's going to be somebody in the audience that says, what about the other one? What we have to think about them jointly. And you as students and as scientists and as engineers, I hope, are thinking about them jointly. Let's start with trees because that's the most popular topic in when you talk about this in public. Trees and soil, natural solutions, we'll call them. Soil first. Soil does not store carbon. Soil is a place where carbon is in flux. A healthy soil, any farmer will tell you that a dark soil is a healthy soil. It's dark because it has a lot of carbon in it. And that carbon is being put into the soil by the roots, both by metabolic processes and by the death of roots. Roots exchange carbon with the ecosystem. They exchange carbon with the plants or the microbes that are in the soil. And the exchange is ongoing all the time. If you turn off the plants, if you turn off the microbial ecosystem, the soil dies. It will not have carbon in it. So soil doesn't store carbon. Carbon-rich soil is healthy soil. It's soil that has active metabolic processes in it. And those soils that we've used for farming to feed us around the world have lost an enormous amount of carbon, mainly because of bad agricultural practices, because we plowed soil and left it uncovered during the winter, because we basically overused the soil. But carbon isn't necessarily extracted by farming. It's just bad practice that allows it to disappear. And the question is, if we use good farming practices, can we put it back? You'll see that the orange zones here are the places where we've had intense agricultural use for the last couple of hundred years, and those have lost a lot of carbon. If we could put all that carbon back, 487 equivalent gigatons of CO2, if we could put it all back tomorrow, we'd be done. We wouldn't have to do anything more, but we can't. We don't know how to do it that fast. And in fact, most agricultural soils are still losing carbon. So that's a huge challenge. Trees, a lot of people would say, why don't we just let the trees do it? I'm from California. I hear that a lot. Well, these 40-year-old redwood trees are just about hitting their stride. They are at their maximum rate of carbon removal. And the magical thing about redwood trees is they will continue removing carbon at an increasing rate every year for the rest of their lives. Most trees don't do that, though. Most trees will hit a maximum where they'll hit a senescence, what we call, where they'll stop removing carbon as the forest gets old. But the question is, are they enough? No matter how good they are they going to do the job that we need to have done? There's problems with that, and I'll point to a really obvious one. In California, you've all seen, we have forest fires. Those forest fires are now spreading into most of the rest of the West as we have periods of extreme drought and beetle kill that tend to drive susceptibility to fire. In 2020, we lost 106 million tons of carbon dioxide from our forests into the air. Today in California, our natural and working lands, independent of this loss from fire, are losing carbon every year. So we would like our natural lands to be absorbing carbon and playing a role in that graphic that I showed you at the beginning of the talk, but they're not today. In fact, our natural lands are losing carbon. They're not contributing yet to the solution that we need in order to hit our temperature targets. If we could get that to happen, if we could preserve the forests we have and take good care, better care of the forests that we have, we could probably get about 3 billion tons a year worldwide. Some people argue it's bigger than that. I contend that I would love it to be bigger than that, and we should encourage that. But right now, it's not. Right now, it's a negative number around the world. One of the things that would be beneficial is it turns out that fire in many of these forests is a function of the fact that we've been fighting fire for so long, and we let the forests grow back willy-nilly after we logged them in the 1900s. And that results in a lot of small trees in between these big trees. And if we remove that small material, it reduces the fire hazard. It also increases the ability of the large trees to grow, and it increases the amount of water that the forest absorbs. There's less runoff. And in general, a healthy forest is one that has large trees in it. And that's a great answer. We should be fighting fire by reducing this willy-nilly growth of material, which is not natural. It's there because we fought fires, which would normally be removing it. And one way to remove it would be to, of course, let those fires continue. That's difficult now that we've let it go so long. The fires get big, they burn the big trees as well as the small trees. But that process leads to another interesting option for us, and that is in the course of removing the wood from the forest that's fueling these large fires, we're removing a lot of carbon. This waste product that we're removing in California, we'd like to be removing 15 million tons a year. We're not up that far yet, maybe about 1 million tons right now, most of which gets burned. So the carbon returns to the atmosphere. And that doesn't really help our global climate situation, although it helps the forest fire situation in California. So this leads us to our second technology option. We've looked at natural solutions. Now we're looking at a more engineered solution. What if we take the carbon that's in biomass and use that as an energy source? We've talked about that for a long time, understanding carbon as an energy source. But what if we use it as a carbon source? But we can also make products like hydrogen at the same time. And this is important because this now becomes a sustainable source of energy, but a sustainable source of carbon removal from the atmosphere. And there's a lot of this kind of biomass available. This is a chart for California. Has about 58 million tons of waste, not any new crops or anything, and not removal from a forest, which isn't going to be happening for either ongoing forest management or fire control that we want to do in the future. That's the red bars that you see up in Northern California, where most of that is. The orange or yellow bars in the middle of the state are agricultural waste. You know that we throw away 1 million tons of almond shells a year before you even get them in your snacks. We've removed 1 million tons of shells, huge amounts of agricultural waste in California. Blue is trash. Of course, more trash in Southern California, where most of the people live. That trash is about 70% biogenic material, 70% organic carbon. And that's a source of carbon that was in the atmosphere recently. And if we let it return by composting, basically breaking down in a trash dump, then we're going to return that carbon to the atmosphere as well. So these are all sources of biogenic carbon that we can use to remove carbon dioxide from the atmosphere. And that removal is surprisingly economic with a little bit of policy support. This is the value of CO2 as a function of carbon price. And of course, that increases with carbon price. But typical carbon prices in the country today, in California, the cap and trade system is running at about $20 a ton. So we're below the energy value for many of these things. But the low carbon fuel standard value is at about 100. And in the current federal legislation, the prices that you get for federal support are all above $100 a ton. So at this point, the carbon in those wastes is worth a lot more than the energy. Even if you could convert them to oil, which you can't directly convert these into oil, the carbon is worth a lot more. So this is a business opportunity right now. Today, it's worth money to you as a business to get into this, removing the CO2 permanently from the air by using these waste feedstocks. And I want to look in detail at one particular process that does that job. And that is turning that biomass into hydrogen. And my favorite way is by gasification, which you can all talk about separately. I'm not going to go into in detail here, but let's look at the various ways that you can make hydrogen for the economy that we're going to need in the future. Electrolysis, just breaking down water into CO2, would have a carbon footprint of about 0 if we use renewable energy to do the job. Today, though, almost all of the 12 million tons of hydrogen that are made in this country are made with what's called a steam methane reformer. We take natural gas, break that methane down into hydrogen and CO2, and then we just emit the CO2, and that results in a fairly large carbon intensity for that hydrogen. It's really not particularly climate beneficial to use hydrogen that's made by SMR because so much CO2 is being emitted in the process of making it. But with better design of those steam methane reformers, which is we know how to do that today, we could capture a lot of CO2 from just existing SMRs, and that's being done in Texas at Petronova today. It's a plant that's off right now, but is going to come back online. And that could cut the carbon footprint more than in half. But what if we designed those SMRs for capture so that they really did a good job of capturing? The term of art here is if they're autocatalytic or autothermal. Basically, if we did all the combustion inside the device and captured the CO2 from that, instead of using external heaters, which is very hard to capture the CO2 from, we could get the CO2 footprint of hydrogen down pretty close to zero. We could capture almost all the carbon that's involved in making hydrogen from natural gas. But what if that natural gas came from biogas? What if it came from a digester that is on your sewage plant or on your biogas from a dairy facility, which are very common today? There's a lot of CO2 and methane being emitted from those. What if you captured that methane and put it into this process? Then the carbon intensity drops because you're capturing some CO2 before the carbon actually gets into the SMR, drops to -7. Or if you started with biomass, like I was showing you with the forest biomass, we could get down to -20. What does this mean? This means that for every kilogram of hydrogen that you produce, there's 20 kilograms of CO2 being removed from the atmosphere. So now we have a truly carbon negative process. People are looking at doing this. Air Liquide's building a process that does this in Las Vegas right now on biogas. So this is a thing that we're talking about, providing the hydrogen that we need, and at the same time doing this job of removing carbon dioxide from the atmosphere. 2 for 1 is always a good idea in any economic evaluation. Third process that is important here that you're going to hear a lot about is direct air capture, building machines that remove carbon dioxide from the air. You'll hear people refer to this as DAC, direct air capture. I hopefully won't do that in the course of this talk, but if I do, that's what I mean. This is one that's operating in Zurich, Switzerland today at a small scale, but it works. We know how to build these things, and they're expensive, as you might imagine from looking at all that engineering. Trick is, can we make it cheaper? The company that built that, Climeworks, is working on that by building bigger plants. This is a 4,000 ton per year plant that they just brought online using geothermal energy in Iceland. Works great. Still too expensive. Well, not too expensive. What's too expensive? How much are we willing to pay? It's more expensive than a lot of people would like to pay for this kind of a service. And one of the things that I'll point out to you is that learning on processes like this is not really complicated. We can look at the nature of the energy that goes into this direct air capture process, and those geothermal processes that I showed you that Climeworks is using have a different learning curve than the gas-fired processes that Carbon Engineering is now designing for use in Texas. They're looking at building large-scale in the Permian and also at King Ranch near Corpus Christi. The reason the two learning curves are different is the size of the actual units that get built. The more units you build, the more learning you get. So if you're building large, efficient units to begin with, you're going to learn slower. If you start with these more inefficient, smaller units that Climeworks is building, you learn faster at the beginning, but ultimately it's a question of how many units you build that will drive the learning to the lowest level. And learning curves like this are very simple objects. They're just every time you double the number of units produced, you increase learning by a certain fraction. And the fraction that's commonly used for units like this is between 12 and 15%. These are about 15% learning curves that I demonstrate here. So that's how fast you can drive the capacity to higher levels and drive the cost down. These are large numbers, though. You need a lot. Look at the bottom axis there. Millions of tons globally deployed, capacity, 20, 30 million tons of capacity required to drive the cost to a lower level. So what's going to happen in the United States? Well, one of the biggest factors in the United States is the electricity that runs the process. We'd love to build this kind of process in Wyoming, and Wyoming's very interested in having that. You look at the electricity, though, it's very dirty there. And so it's actually nearly impossible to build direct air capture that's run on electricity today, or that runs on renewable power of any kind, because you still have to back it with grid power when the renewables aren't available. Very expensive. Texas, a lot better because the grid's better. And there are some areas that have a lot of either renewable or hydropower that are even better than that. That's going to be important for where these kinds of processes get built. But geography is not just important for the electricity that's available. Also, we need to have the land availability. We need to have geologic storage, place to put the CO2 after we've captured it. And this is a study we've been working on at Livermore, looking at where the most propitious places are to build this. And you're going to see it basically along the same axis where you see massive amounts of wind power being built today in the center of the country. And we think California, the Central Valley of California, is going to be good. These are all places where there's good geologic storage available directly underneath the sites where you want to build the direct air capture. And ultimately, the rest of the country can benefit as well. There's a lot of nuance to start engaging things like heat pumps. And if you don't have transport and storage, this is the kind of map that you could eventually end up with where direct air capture looks cost effective around the country. Well, in the course of doing work like this, we evaluated what California's options for doing this are and what it might look like by 2045. What are the options for the state by 2045? And what we found is the three big categories that I've mentioned all can play a role. Natural and working lands, if everything goes really well in California, might contribute 25 million tons a year of removals. As I said, today, they're contributing nothing. So we have to do a lot better than we're doing today, but it could be as much as 25 million tons. But it can't do the whole job. We need a lot more than that. This waste biomass to fuels with CO2 conversion can play a big role in California because we have so much waste biomass. And frankly, a lot of places have a lot of waste biomass, but the forests are important to us because we have to do that anyway. And finally, direct air capture can still contribute some of the 125 million tons that we believe is going to be needed to get to California to net zero, to get that green wedge that I showed you at the very beginning. For California, it's going to take all three of these, and at these, well, these are the maximum amounts that each one can contribute. It's a supply curve, though. The actual amounts depend upon what policies get implemented. But if you get the maximum amount for each element, this is what that supply curve looks like. Natural solutions are the cheapest at about 11 million tons on average. And then in the middle, you see all of those things that are based upon extracting the carbon from biomass. They're relatively inexpensive for two reasons. The processes are pretty well known today, but also you're sharing the cost between two things. You're providing a valuable product, in this case, almost always hydrogen, because it's the most valuable product you can make, and then removing CO2. So the net cost for CO2 removal is the balance of those two things. And so you're not only paying to remove CO2, you're getting a product. At the end, the far right, you see the costs for direct air capture, which even with a lot of learning, are still expensive. They're always going to be the most expensive way that we have to remove CO2 from the air. So why do they get so much attention from policymakers and the public today? Well, I think it's simple. It's that they solve the problem that is. They don't require an engineering degree to understand that there's too much CO2 in the air. We build a machine that takes it out. It does it. Okay. So we always have to remember that sometimes a simple solution can be a very compelling solution, and it certainly is today to policymakers. These intermediate range of things that are based on biomass, carbon removal, and storage, which we've coined the term BIKERS. You may have heard the term BECS, bioenergy with carbon capture and storage. We don't like to use that at Livermore because it emphasizes the energy. And wood is a crappy energy source, but it's a great carbon source. So we want to emphasize using our biomass as a source of carbon to solve our climate problems, and along the way, getting some energy to offset some of the costs. But we still have to do something with all that carbon. What are we going to do with it? Well, our natural solutions take care of it naturally. And between forests and soils, we might be able to get between 1 to 5 billion tons of removals per year. Again, if things go really well around the world. They're not going that well today. But let's see if we can fix it. Still not going to be anything like the between 10 and 20 billion tons that I showed you at the beginning. Put it back in soils, enormous capacity, but it's much slower. But if we could figure out how to do it, could really do a lot of the job. We can put it underground as a liquid. I'm going to talk about that more as a moment. That's what this guy to the right is doing. Or we could make products out of it. We can make carbon-based products out of that CO2. We'll talk about C and D here in the next section of the talk. A lot of the CO2 is going to have to go back underground. The good news is when CO2 is deep underground, when it's a mile down, when it's under that much pressure, it turns into a liquid. Its properties are very similar to oil. It can be stored in the same rocks that have held oil or that are similar to the rocks that have held oil. And perhaps the best news is that the technology, the people, or the jobs are the same for both. So we're not talking about just eliminating fossil fuels in the future. We're talking about some new things that can replace those jobs in the same places. And that's so important. We can't just say to people, well, we're not going to be using gasoline anymore. Go away. That's not good politics. It's not good science. We need to use the skills and we need to use the geology that's available to solve this problem. And I believe that we're going to be able to do that. But is it safe? People worry about this a lot. Anytime you talk about a large new thing that people don't understand, we have to talk about why it's safe. And how we talk about that is extremely important. And I want to spend a moment to emphasize this to you because we can talk about it in ways that don't make people feel like it's safe. Geologic storage of CO2 is a liquid. We should not talk about supercritical CO2. If it's critical, if it's bad, it's supercritical, it must be really bad. Let's just call it a liquid. As scientists, it's fine. It's going to be below 3,000 feet in depth. It's enormously far below any groundwater. And the rules that we have in the United States are extremely strict. We have the most stringent CO2 storage regulations in the world. We have all the knowledge to do this safely. This is a thing that we understand how to do. Most importantly, it's regulated to be safe. I equate this to building 10-story buildings. We routinely build 10-story buildings in the United States because we have good regulations. We train the architects, we train the builders, we inspect when we're building these things. And unless you live in a condo in Florida, we inspect during the history of the use of the building too. And that's the same things that we're going to have to do here. And frankly, we have to learn lessons occasionally when things fail. How do we do it better? But that's what we need to do with CO2 storage. We're not going to depend upon the science to make it safe alone. We're going to depend upon regulation to make it safe. And this is a map that actually Sue Havorka made in a process, a project that we're working on to look at national options for negative emissions. Everything in green are places where we know that there's going to be good geologic storage. The darker the green, the less expensive it is. The closer we can put the wells together, the more certain we'll be when we drill a well that we're going to have a good storage zone. You all know that when you drill an oil well, they're not always perfect. Same will be for CO2 wells. The more green, the more certain we're going to be that's going to work well. And it's not an accident that Southern Texas is the nexus of those sites. We know those are going to be great places to store CO2. Central Valley of California, these are the places where the oil industry was created in the United States. And not an accident that CO2 can go back into the ground and stay there safely, just like the oil stayed there safely all those many years. In yellow are regions that are likely to be good for CO2 storage, but where we haven't been able to quantify it yet. And so therefore the cost is likely to be higher because we'll spend some time quantifying it, but we may be able to store CO2 in all those regions as well. That's good news. Much of the country has good storage. In other parts of the country, we're going to have to transport the CO2 to those regions if we want to store it underground, which I think we're going to need to do. A lot of people, though, will look at this and say, well, why don't we just use that CO2 for something? Why can't we turn it into like the carpet that many of you are sitting on right now is made out of oil. Why shouldn't it be made out of CO2? Why can't the carbon that goes into that product be made from carbon in the air? And it can. It absolutely can. What if we could take the renewable electricity that we're going to be making so much of and use it to create products like ethylene, that's the backbone of all the carbon products that we use in the world? Why can't we make that from CO2? Well, we can. We know how to do that. And that's something that corporations are scaling up today so that we can make more of the carbon-based products that we need out of CO2 instead of out of oil. But for the climate, one of the problems with that is many of those carbon products have a short life. And for plastics, of course, their long life is actually an additional problem in some cases if they don't get managed safely. But the short life of those carbon products is a problem in terms of the climate impact that we want to have. Remember, we have to be removing carbon from the atmosphere throughout the rest of this century. And so if we remove it by making a product out of it, it has to stay removed. Well, let's look at how we should think about that. The carbon that goes into any product is a function of the actual carbon that's in the material, which mostly today comes from fossil carbon. So it's the material that comes from the fossil carbon, and the energy that we use to make that product. So the total climate impact, total carbon footprint is the sum of those two. So that's the thing that we're trying to do better with today. If we substitute low carbon energy, we reduce the total carbon footprint. It's better. So making products with fossil carbon material, but with renewable energy, has a lower carbon footprint, but still not zero. We're still emitting carbon because that product is going to break down over its lifetime and re-emit the carbon to the atmosphere. Still, we should do it. This is still better. If we look at modern chemical factories, they could utilize a lot of CO2. This facility that's being built in Pennsylvania is going to emit 2 million tons of CO2. But if we used carbon to make the products that this facility is going to make out of natural gas, we could utilize 4 million tons of CO2. But as we just saw, it's only a partial reduction because it's going to get re-emitted. Well, if we convert CO2 from a facility like that, and now we use energy to convert, it costs us energy to convert that CO2, make the fossil CO2 material, starting material that we would otherwise use, for instance, make ethylene out of it, add the low carbon energy to make the products, we now have a better outcome. It's a slightly lower carbon footprint than we'd have if we just used oil, but it's still not anything like the net zero that we need to have for a future economy. So this is a good idea as a transition plan, utilizing CO2 that is being emitted by our fossil using facilities today, but it's by no means a net zero solution. One of the things that we could do is take that CO2 and put it back into more permanent products like cement. Well, so here's a modern cement factory that emits about 1 million tons of carbon dioxide a year. There are schemes to reintroduce CO2 back into that cement, which we could, about a fifth of it could go back into the cement. So this cement plant could remove 200,000 tons, but still emit 800,000 tons on balance. Conclusion from that is that utilizing fossil CO2 is beneficial, but it won't meet our long-term climate needs. It's a transition, but it's not a permanent solution. Well, what's a permanent solution look like? Well, what if we got our carbon from some of those atmospheric sources that I talked about at the beginning of the talk, either from biomass or from a direct air capture facility? We're going to have the carbon is now net zero because it's coming out of the atmosphere. And no matter when we re-emit it, we'll still be on balance zero. We still have to pay the conversion energy cost of both capturing the CO2 and making the product we're talking about. But now the products that we would make will have a much reduced carbon impact. And so this is something that can get us close to zero, not exactly zero, and that we look to in the future. And major oil companies are looking at making the products that they want to sell to you in the future in this way, by capturing carbon dioxide from the air, turning it into the products that we all use. And of course, the longer lived those products are, the more beneficial this is for the climate. But corporations are looking at emissions from different ways, and I want to walk you through one that's really important. Microsoft's an example of a company that wants to get to net zero as quickly as possible. And these are their emissions and their plan for getting to zero in the future. What are their emissions? Not very large. They max at about 15 million tons a year. Most of those emissions, though, interestingly, come from you and I. They come from the computers that we're using right now to watch this webinar. The fraction of the electricity that gets used to run the Microsoft product that Microsoft products that you're running counts as part of their emissions. It's called Scope 3 emissions. That's a term of art that you'll hear, but basically it's the emissions that are associated with the fact that they sold you a product, but they can't control how you use that product. And so in the future, there's going to be emissions. And if Microsoft wants to get to net zero for the whole corporation, they can't tell you how to use their product. So they're going to have to remove carbon dioxide in order to offset, or basically remove, the emissions that you're emitting right now. And so that's a really important part for a lot of company strategies, is to remove CO2 in the future. It's important because of customer use. Supply chain is also really important. And for a company like Microsoft, this is a relatively minor thing, Scope 3, 15 million tons. If you're Shell, the use of the product by the customer is the use of gasoline and oil, and it's 500 million tons. Very difficult problem. Probably can't get there by removing those emissions from the atmosphere later, at least not at an affordable level. This is a challenge today because companies want to purchase these removals, but they're not available. They can't get long-term removals, even at any price, let alone at a reasonable price. So this is a big challenge, and this is one of the things that's driving the negative emissions industry today. Many of the examples that I just showed you are being paid for today by companies like Microsoft and Stripe and Shopify and other companies that are purchasing these removals today. What are some of the elements of what we call a durable removal? Durable means it lasts long enough to make a difference to the climate. So it's removed from the air. It's not a fossil source. It's stored in a form that doesn't return to the air very quickly. Let's say 100 years. There's a lot of discussion about what that number ought to be, but 100 years is pretty long. It's, for instance, most products, you certainly can't make a fuel out of CO2. It'll return to the air this year. That doesn't count. And where there's a good assessment, a life cycle assessment, you're all going to learn way more than you want to know about life cycle assessment and the importance in these kinds of economy. But everyone says, who's going to pay? Well, just like trash removal, we're all going to pay. The good news is that it's not that expensive. Let's walk through this a little bit. Current world GDP is increasing about 2.5% a year, but the costs of doing all these jobs that we're talking about are decreasing because we're getting better at it. Even if none of them saves any money, and if they stay at the same cost they are today, neither one of those is going to happen. Our 2050 cost would be about 3% of GDP if we used it to remove all the 60 billion tons that we're emitting today. Today in California, we spend 3% of our GDP taking out the trash, literally not throwing our trash in the street, but taking it to a landfill and putting it away safely, 3% of GDP. These are affordable things. These are things that are going to happen in the future. The world's going to do these things, and you all as engineers are going to help them do it. The limit is going to be capital. Carrie and I were talking about this a little bit before the talk. This is a big deal. Is the capital available to do that? Well, the world reinvests about 24% of GDP per year. And let's say we need 4 trillion in investment to do this. Again, we can manage that over 20 years, but that 4 trillion is, of 40 billion tons. These are all difficult calculations to make. I'll let Carrie tell you about the details of how to do so in a much better way. But the point is, these are not out of target. When people tell you it's too expensive, it's because they don't want to stop doing what they're doing. These are all people who are making money in today's economy and haven't figured out how to make money in a future economy that's good for the climate. And capital is the most important thing in all of these new systems. The fraction in dark blue here of this report shows the amount of capital that's required for the total cost. And you'll see for almost everything, it's the capital cost is what really matters. And that makes sense. The wind is free, the sunshine's free. It's building stuff that matters, but you still have to build a lot of stuff. And I'll point out an important factor. China does not set its capital cost based on market factors. It just makes it up. They set the capital cost for the next 5 years, and then that's what companies in China pay for capital. So they get an entirely different economic game than the rest of us have to work with. But this is not the only constraint that we have. We do a lot of things based upon optimizing money, but that results in a lot of harm to a lot of people and a lot of historic harm that's been done in building out large energy infrastructure that we're hoping to avoid in the future as we change to a new energy infrastructure. One of the first things we have to worry about is that fossil fuel jobs are a huge part of the economy of this country. How are we going to look to places that have those jobs today to be part of this new energy economy in the future? Well, as you saw from my map earlier on direct air capture, that maps pretty nicely. So that's a good one. That's one we can look to do a good job of helping with that kind of issues. But there's a lot of other things. In particular, when you talk to environmental justice communities about these things, they're very worried about air pollution. They're very worried about health. We have to be able to answer those questions. We have to be the lower graph shows a potential water pollution from using biomass as an energy source. We have to worry about that. It's enormously more complicated than just thinking about the cost of building stuff. We have to build stuff that we want to live with. We have to have communities that we want to live in. We have to have healthy people. We have to take care of our world. And that leads me to my final message, which is all of you, I encourage you to keep a big tent. Everything that I've talked about and a whole bunch of other things are going to be important. It's really easy to focus on one thing and say, oh, that's the most important thing. Well, it's not. Everything's important. You can't be an expert in everything, but you can keep a big tent and absorb what other experts are doing, absorb what people in the community who are concerned about what you're doing, why they're concerned about it. We need to both educate the public and be educated by the people who are going to benefit and suffer from the changes that we make in the future. I encourage you all to think about your future in that regard. And with that, I'll turn it over to Carrie and questions.
Okay, thank you very much, Roger, for that, I think, very nice and quick overview of the big scope of, CO2 capture from the atmosphere and getting to net zero. So, we do have a few questions here, so we'll work through them. A couple of things on just your mentioning examples of projects going on. One here is, can you confirm, you talked about an air leak plant, I guess, that's getting constructed in Nevada or Las Vegas. I'm not sure what you said. I think it was a biomass. And the person was asking if it was a carbon capture associated with that. It's a simple question.
Not yet.
No.
That plant is going to use natural gas, renewable natural gas that comes from anaerobic digesters around the country to make hydrogen. But they're not capturing the carbon dioxide yet. This is something that the new incentives to do this have just come online from the federal government. And all these companies are scrambling because they realize that the carbon is worth more than the hydrogen from that plant. So they're unfortunately building in Las Vegas. I don't know if you noticed the map, Sue Hovorka's map of geologic storage, not Las Vegas. So that's the kind of thing that's going to really be part of the equation in the future.
Yeah, incentives versus geology, I guess. You also mentioned the Petronova plants coming back online. Is there anything you can say about that? It was, I think some of people are aware of this. It was a CO2 capture plant on a slipstream of a coal plant outside of Houston, and it was using CO2 for EOR, and then they shut it down due to economics. And you're saying they're going to bring it back now?
They are, because of these incentives that are available from the government for storing CO2 underground. It's making you're not relying on just selling the CO2, you're relying on these federal incentives, and that's going to be a huge part of the economic incentives for anything around fossil infrastructures. Basically, if you can capture the CO2 from it, not emit it into the air, it's going to be much more economically attractive, as Petronova is now.
All right. I'm going to ask this. I think you kind of addressed this question, but you can just elaborate perhaps a little bit more. The question: what are your thoughts on the validity of nature-based carbon sequestration? There's been some skepticism regarding the amount of carbon sequestered by these projects, perhaps ideas of double counting carbon sequestration and nature-based solutions. I think you went over some of the numbers, but anything more to elaborate on this, or the difficulty of counting nature-based carbon storage?
It's a huge problem. I am very fond of nature-based solutions. They're good for the country, they're good for the nation, they're good for the economy. But they're not being handled very well today. And I'll tell a short story about that. The Nature Conservancy owns forests, particularly in the East Coast. And early in the process of thinking about this, particularly when California's cap and trade system came online, intermediaries approached Nature Conservancy and said, would you like to be paid to protect your forests? And Nature Conservancy is like, of course we would. And so they began selling credits to these intermediaries who sold the credits to fossil fuel interests in California. Well, it turns out that when you look at these things in detail, nothing was happening because of that. The forest was already protected. And so let's say Chevron bought those credits because they were emitting CO2 in California, but the Nature Conservancy was not absorbing any additional CO2. It was not an additional, it's called additionality, and caused a huge flap. And Nature Conservancy was very embarrassed because they didn't intend to cause a problem like that. They're like, we were protecting our forests. But things like that really matter. And it turns out that when you look at nature-based solutions around the world, a lot of them have that problem, that they don't meet the standard of the money went to remove CO2 from the atmosphere. And it's a real problem. And there's over the next year or two, there's going to be a huge flap about that from scientists like me who are calling BS on those kinds of projects, which doesn't mean that nature-based solutions aren't a really, really good idea, but they have to be done well. And it's the intermediaries that are screwing it up, frankly. They're people who just want to make money, and so they'll push anything and sell anything. And I apologize if any of them are online here, but you need to do better if you are.
All right, thanks for that elaboration. Here's a question kind of about analyzing, I guess, energy carriers. You're focusing on carbon, but you're also mentioning hydrogen and biogases and renaming BECCS to focus on the carbon. So the question is, can you elaborate? You can take hydrogen as an example if you'd like. Any analysis you do at the lab on what we call net energy analysis or energy return on invested, and understanding how changing to these other fuels from traditional hydrocarbons, for example, affects your analysis, or is it just an extra analysis, or is it integrated? Anything to say about that?
We do. Two comments about that. The first is that we've all been trained to look at the economics of these processes. And so that immediately leads to disbelief when we talk about capturing CO2 from air and turning it into a fuel. Why would you do that? It's energetically ridiculous. Well, it turns out you might do it because it creates the environment that we want. We're paying to have the environment that we want. And so we do analyze that because we don't want to be more ridiculous than we need to be. We need to take that into account, but we also need to remember that we're getting more than one product in doing that. We're getting a healthy environment. I actually think that making fuels from direct air capture is a long way from being energy efficient. Might make more sense to just take those electrons that we get from wind and solar and put them directly into electric cars. But then there are people who want to make fuels that sell fuels, and they're like, wait a minute, we can do a better job. Well, great. If they can, I think they should. And it's not to say that we have to all run on battery powered vehicles in the future, but we do have to consider the economics. Second thing, though, that I'll emphasize again is that we shouldn't make every decision based upon money. There are other reasons that we're making these transitions, and the lowest money might be the worst environment.
Right. That's a good statement. I think that's for a whole other discussion. So here is one on your kind of, I think, interesting, Microsoft versus an oil and gas company, Shell example. The person's asking, how can both digital product and energy be scope 3 if I use a generator to run a Zoom call, or perhaps if we're using Microsoft Teams or something like this? Is that Zoom's or Microsoft's scope 3 emissions, or is that the coal company or natural gas or electricity company's scope 3 emissions? That may be too large of a concept from life cycle assessment, but any thoughts on that?
I think in a proper life cycle assessment, those would be apportioned among all those different parties. It's very difficult to do. So a company like Microsoft tends to be conservative in doing it. For a company like Shell, it's much more straightforward. They sell you gasoline, you burn the gasoline, it goes into the air. That's their scope 3 emission. It's your scope 1 emission. There is an overlap in those things, and that accounting has to be worked out. I am not going to burden your brains with it because, frankly, my brain doesn't work that way either. I think the point is we all have a responsibility, and I'm really glad to see companies who have those kind of funny, tenuous responsibilities stepping up and saying, yeah, we're going to take some responsibility.
Yeah, you made me think of a side note. I mean, a lot of the role of federal government, including Department of Energy labs and national labs, is standards or NIST, standardization of things. Is there any discussion of standardizing these scope emissions, at the countrywide level to make sure you don't double count when you run all the numbers? You got to get the same amount of emissions. Okay,
it's a big deal in the current funding from all these federal projects, particularly the Inflation Reduction Act, which pays people to do all these things. They want to get those numbers right. So there is funding to do that.
Sounds good. Here's one from YouTube watcher. So this is about municipal composting. How do you have a feel for how much nationwide, composting can do in terms of absorbing CO2? And do you think it would be important to have some kind of regulations or incentive for compostable packaging and collection of municipal waste at cities? Austin has a sort of net zero waste plan, so they instigated compost collection at houses. But anything about composting?
Composting is a difficult one for those of us that want to have a good environment. Composting is really good in terms of reducing trash, in terms of reusing the products that we have today, making it into fertilizer, et cetera. However, first of all, most of that composted material does not go back on farm fields because it has other hazardous materials associated with it. So that's difficult to do. And the carbon ends up back in the air after you compost it. So that's a tough one. That's one of those ones where we have to say, wow, that's the yin and yang of composting. How much of it do we want to do? How much do we want to control that? There's new companies now that are trying to capture the carbon dioxide from composting. I'm all in favor of that. Then we get both benefits, but that's the kind of complexity that you're facing.
Right. Here's another question. Maybe you slightly adjusted already. It's slightly different. It's kind of more about, I guess, accounting, carbon accounting, life cycle. companies having subcontractors that provide things for them and this kind of thing. So how do we account for companies that might be offloading their emissions to other companies? Is this just kind of being conservative, like you're saying Microsoft is, and trying to be honest, even though they might do some double counting, but Lawrence Livermore at the national scale helping us do all the accounting at the entire national scale?
Actually, the accounting standards for that are pretty good and pretty straightforward. If people choose to follow them down all the various rabbit holes that creates, the standards are pretty clear from industry groups that have put these standards together. So that one, I don't worry about. What happens, though, is that companies will run through all that, and then they'll say, our carbon burden is 10 million tons, and then they'll buy 10 million tons of reduced deforestation in Brazil to offset it. And that's complete BS. Nobody's reducing deforestation in Brazil. It's not happening. So, that's where you did all this all this complicated accounting, and then you offset it with something that isn't real. Oops.
Right. Let's see. It's a question about sort of something that happened at the beginning of the webinar, where we take our carbon out. So do you think implementing efficient public transport across cities will help take carbon out of the atmosphere, or will this not work due to behavioral decisions? Or I don't know, maybe in general, transportation and carbon removal. I guess you talked about aviation being a hard to decarbonize activity. This one may be more, ground transport, but anything more about either of those?
Yeah, this is the challenge for those of us technologists. This is our job, is to make those options available to people so that they have an option that they can use that makes sense to them. They want to ride the bus, great. If they want to have a car that doesn't emit, great. If they want to run on liquid fuels that don't have a carbon burden, great. But we can't, as technologists, tell people what they want to do. I see this a lot in my friends and colleagues. They're like, if only people would do this. And we're like, guess what? That's not our job. Our job is to make the options available to them. And I hope that you all will take that kind of attitude as well.
There you go. And here, maybe we'll end on this one. Talked about carbon storage and soils, or healthy soils and forests. And this question's about, is there any potential for absorption in oceans? I guess we're already getting CO2 stored in the ocean, maybe more than we want, but yeah, store it in the right way from acidification. Or how do we think about oceans? Yeah.
Oceans play a huge role. 60% of the CO2 we emit ends up in the ocean. So it's already happening. The problem is it has deleterious effect. It's acidifying the ocean because it's too much. What happens to CO2 normally in the ocean, over time, it turns into limestone and removes itself from the chemistry of the ocean. This is good news, but that's slow, and we're adding it too fast for that to happen. So there are people who are trying to speed up that process. That is really just a new field of scientific research. I encourage it because the ocean is such a big participant, but we can't really say yet how successful that's going to be. But what I say about all these technologies is we need everything we've got, and then we're going to need some more. So I hope people are going to develop those ocean methods as well.
Right. Okay. Well, I think we'll end it here. So thank you very much, Roger Aines, Chief Scientist of the Energy and Homeland Security Program at Lawrence Livermore National Labs. Thanks for joining us here.